Yeah. So today we will going to start with module 5. So where we have to discuss the concept called dynamic programming. See, in this, why I have taken this module is relatively easier because the syllabus or the content what we discuss is little less, and also the problems, the variety of problems are less. It will be easy for you people to prepare because once I take you for module three it is a very big module. A lot of methods are there, a lot of approximations are there. So therefore, instead of taking to the module 3, I will take you to the module 5 from today. And let me complete this module 5 quickly. And later part, we will come back to the module 3 and module 4. So in module 5, so we need to discuss the concept called dynamic programming. So let me just overview or give a brief description about this concept of dynamic programming. So basically, in this dynamic programming is a multi-stage decision process. So in the sense, so when we want to have to make the multiple decisions at a domains or decisions at various stages of engineering applications, so we can use this concept called dynamic programming. Okay. So here, so what we do here is in the total entire system will be divided into a subsystem, and we start optimizing the each subsystem, and ultimately it will be going to lead to the optimization of the entire system. So this is a basic concept or principle what we have been employing in the programming called dynamic programming. Okay. So in this dynamic programming, at the outline, so we need to have to discuss an introduction about dynamic programming and multi-stage decision processes. We have principle of optimality, computational procedure in dynamic programming, and at the end we need to have initial value problems, and also we have certain examples in the sense the solving linear programming problems using the dynamic programming, and how to solve nonlinear programming using dynamic programming. So those concepts are going to use, that is only the problems what is supposed to solve. Those things we will going to discuss at the end of this chapter. Okay. So in today's class, let us start with an introduction, and also we will move to the second point, what we call it as a multi-stage decision process. So we need to have certain examples to discuss where the system will constitute for the multi-stage decision processes. Okay, and we need to discuss what are the elements of the multi-stage system and the single-stage system, and what are the different parameters that needs to be discussed. This is what we are going to discuss in today's class. Let's start with an introduction part. In most of the practical problems, so we need to make a decision. So means a decision has to be made sequentially at different points of time, at different points in space, and at different levels for a component or for a system or for a subsystem. In the sense, what it says is, if you take any problem, either it is related to a civil engineering, whether it is related to electrical engineering or mechanical engineering, whatever it might be. So when you are designing a system or a subsystem or a component, right? So there may be a plenty of decisions. Means you need to make the decisions sequentially, one after the other, at different points of time. So not necessarily that every time or at the end of the time you're going to do the decision here. So here what we are doing is we are making the decisions sequentially at different points of time and different levels when we are designing a component or a subsystem or a system. The problems in which the decisions are to be made sequentially are called sequential decision problems. In the sense, when we make the decisions sequential, in the sense when we start doing the decisions sequentially, and such type of problems, we just categorize it as a sequential decision problem. So this is sequential in the sense, one after the other, we start making the decision. These decisions are, since these decisions are to be made at a different stages, they are also referred to as multi-stage decision problem. Either it is a sequential decision or whether it is a multi-stage. Both are one the same. So sequential in the sense one after the other we need to make the decisions. Whereas in a multi-stage we need to make the decision at the different stages. Hence it is called a multi-stage decision process or a sequential decision process. Dynamic programming is a mathematical technique well suited for dynamic optimization of multi-stage decision process. In the sense, so when we want to optimize or when we want to solve a multi-stage decision problems, so dynamic programming is one of the best suited technique, and we will go to understand what is this dynamic programming problem, right? The dynamic programming technique represents or decomposes a multi-stage decision problem as a sequence of single-stage decision problems. In the sense, when you want to use or when you want to apply the dynamic programming problems or techniques, so this dynamic programming technique decomposes multi-stage decision problem into a sequence of single-stage problems. In the sense, it bifurcates the multi-stage into a single stage decision problem. Thus, n variable problem is represented as a sequence of n single variable problems that are solved successively. In the sense, so when we say a problem is n variable problem and a sequence of n single variable problems are solved successively, we are going to solve each one by one. The decomposition to n subproblem is done in such a manner that the optimal solution of the original n variable problem can be obtained from the optimal solution of the n one-dimensional problems. So here, what we are doing is when we decompose or when we just divide, can put it as we divide a multi-stage problems into a single-stage decision problems, or when we decompose an ends of problems is done. So, which will be done in such a manner that the optimal solution for the original n variable problem can be obtained from the optimal solutions for the n one-dimensional problem. So we will go on to discuss this, how we can decompose the multi-stage problems into a sequence of single-stage decision problems, okay? And how we can arrive at the optimization of each single-stage decision problems and how it can lead to the optimization of multi-stage decision problems. It is important to note that the particular optimization technique used for the optimization of n single variable is irrelevant. In the sense, so what technique we use for a particular optimization, so it will be different for different single variable problem. Yeah, so we are talking about multi-stage decision process or multi-stage problems. So now let us define what is multi-stage decision process. Let us define it first. A multi-stage decision process is the one in which a number of single-stage processes are connected in series so that the output of one stage is the input of the succeeding stage. So please remember this. So multi-stage decision process. When you say a multi-stage, so it is just a combination of, it is a mixture of a number of single-stage processes. And each single stage processes are connected in series in such a way that the output of one stage will be the input to the succeeding stage. Okay, it is just like it is arranged in the sequential order, one after the other. That's why it is called sequential problems, or we can say it is as a multi-stage problem. You can take it. So when we want to say it is a multi-stage decision process, so it is the one where the number of single-stage processes are connected in series in such a way that the output of one stage will be the input for the succeeding stage. So this type of process should be called as serial multi-stage decision process, since these individual stages are connected head to tail with no reset. In the sense, so output of one stage will be the input to the second stage. In the sense, output of first stage will be the input to the second stage. So each one, so like that, in a similar way, the output of the second stage will be to the input to the third stage. Like this, so each stage will have their own input and the outputs. Okay, and they are not connected, they are not recycled. Means they are connected from head to tail. It's just like a head to tail without any recycle, without any recycling. So therefore, they call this type of process, the multi-stage decision processes is also called as the serial multi-stage decision process. Okay. This serial multi-stage decision problems arise in many types of practical problems. So let us look at different examples over here. So where we actually consider the process as a serial multi-stage decision process. So where we need to have to make decisions at the different stages. So let us have to discuss some of the examples, simple examples. We're going to discuss it now one after the other, right? So let us take the first example here. So in this example, we have a chemical processes. Example of a chemical process, which basically consists of a heater, a reactor, and a distillation tower which connected in series. A heater, reactor, and distillation tower. Okay, so this is constitutes one serial stage, multi-stage, serial multi-stage decision process. The objective of this process is to find the optimal value of the temperature in the heater, the reaction rate in the reactor, and the number of trays in the distillation tower, such that the cost of the processes is minimum while satisfying all the restrictions placed on the processes. See here, the ultimate objective is to minimize the cost of the process. Minimize the cost of the process and satisfying all the restrictions placed on the process. So when you want to minimize the cost of the process, so what decisions have to be taken at the each stages or each component of this chemical process. So we have three elements. One is a heater, one is a reactor, and one is a distillation tower. And each are connected in a series, one after the other. Heater is connected to the reactor, reactor is connected to the distillation tower. Okay. So in this optimization, when we want to optimize the cost or we want to minimize the cost, so what we have to do is we have to find what is the optimal value of the temperature in the heater. Second one, what is the optimum reaction rate in the reactor? Okay. And the third one is what is the number of trays in the distillation tower? So these are the three important parameters that needs to be optimized in each of the stages over here. Okay. So once you optimize or once you find the optimal values across each stages, okay, then ultimately overall, so you are leading into the optimization of the cost. So here optimization in the sense you are minimizing the cost of the chemical process. So this is a one simple example for serial multi-stage decision process. In a similar way, we have another one example. So this is the example I have shown with a block diagram also over here. So it is just like a missile resting on a launch pad that is expected to hit a moving aircraft in the given time interval. So this is the missile, and this is the target. Okay, so the missile has to hit, it has to expected as to launch pad is expected to hit the moving aircraft in a given interval of time. The missile is resting on the launch pad and you are expecting that missile to hit the moving aircraft in a given interval of time. The target will naturally take an evasive action and attempts to avoid being hit. The problem is to generate a set of commands to the missile so that it can hit the target in the specified time interval. This can be done by observing the target and from its actions and generate periodically a new direction and speed of the missile. Look at this. This is a very simple example we are taking. Missile hitting the target. The missile which is resting on the launch pad. So we expect that missile to hit the moving airplane or aircraft, which we consider is at a target, within a given interval of time. But the aircraft will naturally, it will take an evasive action and it will start attempting to avoid being hit. Means it will take its own decisions that the target will, means the aircraft will take decisions and it will start taking some action. It will want perform certain actions and so that it will start avoiding being hit. But what we want to do here is we need to generate a set of commands to the missile so that it can hit the target in the specified time interval. So how you can generate the command? So our task is to generate the command which will go into hit the target. The missile will go into hit the target within a specified time interval. And this can be done, how we can do? This can be done by observing the movement of the target and its action, how it is, what attempts it is making to avoid being hit. And we need to start generating the new direction of the missile so that it is going to reach the target and what speed it's supposed to hit, supposed to move. In the sense, so we have to observe the target, we have to observe the actions of the target, we need to generate the new directions periodically, and we need to control the speed of the missile. So this is what the task for us. So this is the diagram what we are showing over here. Okay, so this is the missile and this is the target. So missile launch, which is resting on the launch pad, it has to hit the target. So when it has to hit the target, the target tracking radar. There are two radars we are using here. One is a missile tracking record. Second one is a target tracking record. Okay. The main function of the missile tracking record is, so it will go into control. So where the missile, where it is, when it has been launched and how, in what direction it is moving and what is the speed of the missile. So that will to be taken care. When it comes for the radar will go into identify the actions, the movement of the target, so which starts attempting to avoid being hit. So what is the actions that target is being taking? So that signal will be sent to the computer. Okay. So missile tracking and radar tracking, means target tracking, both will be taken to the computer, and computer will send a signal to the radio command line, and it will pass to the missile missile will go into start hitting the target. So it is just like the objective, where objective is to hit, the missile has to hit the target within a specified interval of time. So both are important. Interval and the speed both are in time interval, and the speed are very important, and the target is very important for us. So the missile will be in continuous touch with the computer, and the radar is the one which will go into track the missile, and there is another one radar which will go into track the target. So all these commands will be taken by the computer, and computer will start generating the new commands for making the new directions and the speed. So because the target, the missile has to hit the target within a specified interval of time. So this is what we generally call it as the serial multi-stage decision process, where the decision has to be taken simultaneously, sequentially, okay, so that the missile will go into hit the target. This is what we will go into. And this is one simple example for the sequential or a serial multi-stage decision. Yeah, next we have example number 3. So here we consider a minimum cost design of a water tank. The system consists of a tank, a set of columns, and a foundation. Here the tank supports the water, the column supports the weight of the water and the tank, and the foundation supports the weights of the water, tank, and the column. The components can be seen to be in series, and the system has to be treated as a multi-stage decision. So here, so just like a simple design of a minimum cost water tank. You might have seen the water tanks, very huge water tanks will be built. So to store the water. So when we take that as a system for us, and three main important things. One is the water tank. Second one is the column. I think you might have seen the column. And columns are rested on the support or on the base, or what we can call it as the foundation supports. So here, so we need to design the tank so that the tank can support the water. Okay, and the weight of the tank and the weight of the water has to be supported by the columns, and columns are resting on the foundation. So foundation has to support the column, the tank, and the water. So it has to support the weight of the tank, weight of the water, and weight of the column. So look at that. This is just like, again, it is a sequential decision problems where we need to make the decisions of designing the tank, the column, and the foundations. This is where our optimization or dynamic programming technique will come into the picture, and this we're going to consider it as a sequential multi-stage decision problem. Okay. These are all some of the examples where you can consider it as sequential decision problems. And finally, let us consider a problem of loading a vessel with the stocks of n item. Each unit of item I has weight Wi and monetary value Ci. The maximum permissible cargo weight is W. It is required to determine the cargo load that corresponds to the maximum monetary value without exceeding the limitation of the total cargo weight. Although the multi-stage nature of this problem is not directly evident, it can be posed as a multi-stage decision problem by considering each item of the cargo as a separate stage. So this is what finally what they say is problem of loading a vessel with a stock of n items. So each item, there are n number of items, and the problem here is loading the vessel with a n number of stocks of n items. You can put it as stock of n items. There are n number of items. Each item, each unit of item has a weight Wi and monetary value of Ci, means cost. The maximum permissible cargo weight is W. Okay. It is required to determine the cargo load that corresponds to the maximum monetary value without exceeding the limitation of the total cargo weight. The objective is you have to load the vessel, and the loading can be done corresponding to the maximum monetary value without exceeding the limitation of the total cargo weight. Although the multi-stage nature of this problem is not directly evident, it can be posed as a multi-stage problem, considering each item of the cargo as a separate stage. So this is how we can relate the different real life examples, and we can model it as, or we can treat those problems as a multi-stage decision problems, and we can provide the solutions for such type of problems by using our dynamic programming technique. Okay, these are all few of the examples I wanted to discuss before we go for the representation of multi-decision. Okay. Let us move on to the next one, what we call it as the representation of multi-stage decision process. multi-stage decision process. So before I just go for the block diagram of a multi-stage decision process. So because multi-stage is a combination of a single stages, because it multi-stage process in our dynamic programming will decompose the multi-stage into an n number of single stages. Okay, let us first discuss with the single stage decision process, and later on I will going to explain the multi-stage decision process, how it can be represented. Okay, so what you are seeing on the slide, it is the representation of a single stage decision process. See, generally in our approach, in dynamic programming approach, we represent a single stage decision process in the form of a rectangular block. So, rectangular block. So, this rectangular block or this single stage processes will consist of four important elements. Okay, so one is called an input, second one is called the decision, and third one is an output, and the fourth one is a return. Okay, so we have annotations. We have representing the input, output, decision, and return in a different alphabets. Here we have input or a data, which will be represented as an S, decision in the form of an X, output is the T, and return is the R. So what's happening here is single stage. You are making the decision, the stage transformation, what we are calling it as. So stage transformation is the T, the output, which is the time function of X variable, that is decision, as well as the input. So the output is the function of both the decision and the input, what is given to the block, right? So therefore, so this is the single stage decision process, which is represented as a rectangular block. Okay, so the four elements we'll discuss. The decision process can be characterized by certain input parameters S, capital S or data, certain decision variables X, and certain output parameters T, representing the outcome obtained as a result of making the decision. Okay, so the input parameters, we call it as input variables or input state variables. We call that as an input state variables, and the output we call it as an output state variable. So from now onwards in our dynamic programming problems, S represents input, where T represents an output, where X is a decision, whereas R is a return. Okay, so there are a return objective function R, which measures the effectiveness of the decision made and the output that results from these decisions. So this is another one important thing here. See, when you give an input to the system and you're going to make certain decision, so the combination of a decision and the input will always result in an output. Okay, so in between these three, S, input variable or input variable S, decision variable X, and the output variable T. So there is a one function called a return function, or we call it as an objective function, which is represented by R. So what is that this return function will measures? It measures the effectiveness of the decision, what we made, and the output that results from these decisions. So that is what the return function will go into, or return element will go to be used for. Okay, it is represented as R. The single stage decision process shown in the figure above, the output is related to the input through the stage transformation function, denoted by the output stage variable. So this is stage variable, we call it as a stage transformation function. This is a transformation function, small t, which is a function of the decision variable X and the input state variable S. So this is what the output is related to the input through stage transformation function. So this is called the stage transformation function. So 5.1 represents the single stage decision process where output is related to the input through the stage transformation function. Since the input state for the system influences the decision we make, the return function can be represented as, since the state of the system influences the decisions we make. Okay, the return function. See, once the input is given to the system and once we make a decisions, so the decisions will always influences the state of the system. Okay, so what is the effectiveness of making the decision? So that can be represented in the form of a return function, which we represent it as a R, which is equal to a function of comma, decision variable and state variable. So 5 point. A serial multi-stage decision process can be represented schematically as shown in the figure below. Because of some convenience which will be seen later, the stage n comma n minus 1 comma I to 1 to 1 are labeled in the descending order. For the ith stage, the input state variable is denoted by Si plus 1, the output state vector as Sn. Since the system is a serial one, the output from stage I plus 1 must be equal to the input to the stage I. Hence, the state transformation and return function can also be represented as. I will come back to this later. Look at this diagram over here. Here, this is the multi-stage problem, the initial value problem, what we call it as. So when you look at over here, this is the representation of a multi-stage decision problem. So we have an n stages starting from 1, 2, I, n minus 1 and n. So the input to this stage, the last stage, n stage is Sn plus 1. Okay, so the decision variable will be x suffix n, whereas the return function will be r suffix n. So what will be the output of this? Output of this will be Sn. Sn will be the output for this. Okay. So here we have an output variable S. Okay. So Sn is the input to the stage n, and the output of this will be Sn. And what will be the output of this stage will be Sn minus 1. So like that, we can have n number of stages, and where we have here it is Si plus 1. Si plus 1. So here, so Si plus 1 is the input to the ith stage, whereas the output is Si. And of course, correspondingly, we have a decision variable Xi and the return function Ri. So like this, you can have, so when you just observe here, so comparing Sn plus 1, In plus 1, Si plus 1, like that. So if the stage is 1 or stage is 2, you say stage is 2, so its input will be always S2 plus 1, that is S3, and its output will be S2. Okay, and its decision variable will be X2, and its return function will be R2. Like that, if you look at the stage 1, the input is S2, output is S1. Like this, we will going to connect each of the stages just like from head to tail. It is just like in the series we are getting here. So this is what we call it as multi-stage decision problem. Multi-stage decision problem. So you can understand here Sn plus 1, Sn minus 1, Si plus 1, Si, S3, S2, S1. Like that, they are all input to the, if it is input to the other one, definitely the output of that will be the input to the next stage. So this is how we will going to connect each stages in serially, and hence it is called serial decision or multi-stage decision programming problem. This is the block diagram which is representing multi-stage decision problem. The objective of the multi-decision problem is to find x1, x2, xn so as to optimize some function of the individual stages written say r1, r2, rn and satisfied by the equation 5.3 and 5.4. So this is what I was just about. So this is how we have written Si is equal to Ti of Si plus 1 into Xi, where Ri is Ri, so this is just for ith position, what we are taking ith stage. right stage, the input will be si plus 1 and the decision variable will be xi, whereas for the return function, so si plus 1 and xi. So here, the main objective is we have to find out these decision variables. Ultimately, we had to take out x1, x2, xi, xn. This is the one what we supposed to do it or supposed to determine in our dynamic programming problem. So what is the value of x1, x2? That is the decision variables. So to optimize some function of the individual stage returns. The nature of n-stage return function f determines whether a given multi-stage problem can be solved by dynamic program. Since the method to work as a decomposition technique, it requires proprietary and monotonicity of the objective function. To have separability of the objective function, we must be able to represent the objective function as a composition of individual state returns. So this function, this requirement is satisfied as an additive objective functions. So this is the final equation. So what you can write it. Okay. So this is the function what we can write the things, and we can finally we can how we can write the expression. So let's stop at this point, my dear students. If any have any clarifications, anything, because I got less than 1 minute time. So this is a new concept, new module I just started today. Okay, very simple concepts we are having. So most of things are theoretical based, and a few problems are there. So let me finish off this module, and later what I will take for next the remaining modules. Okay. So module 5, right? I started with module 5, dynamic programming problems. The basic concepts we are discussing here. In tomorrow's class, I will just continue with the same thing tomorrow. So where we need to have different types of multi-stage decision process. If you have any clarification, you can.